Okay, after we have learned about the intermolecular forces, which determine the formation of solid state. Okay, and in solid state, it can further divided into crystalline material as well as amorphous material. So now, after you have recognized crystalline and amorphous material, here we would like to introduce you to the technique of characterization for the solid state. So today we will focus on the characterization technique of solid. There are actually many techniques that you can use for characterization of solid, but the main 5 that you can use are: first, differential scanning calorimetry, or in short you call them as DSC. The second will be X-ray powder diffractions. The third one is Fourier transform infrared attenuate total reflectance, means they use the infrared wavelength. Or you can use observation with optical microscope. Okay, you observe the crystal habits, or you can also observe the crystal habit using scanning electron microscope, whereby you can have a bigger scale of the crystal, that if you look under scanning electron microscope, as the sensitivity will be higher. So in the subsequent slide, we will talk about each and every technique in slightly more detail. So for all the 5 techniques, you are expected to be able to understand the principle of each technique, okay, and how it is used to characterize the solid. Okay, let's talk about DSC, which is differential scanning calorimetry. Okay, as the name implies, differential, this technique compare the unknown, which is your sample, okay, to a reference. Okay, in this machine you have 2 little bowl in the machine, okay, or you call them as furnace, okay, and they have what you call a heat supply, okay, and one of them will be for reference and another one for sample. Let's say you have the heat supply of reference HR, and you have the heat supply of the sample. Okay, and how they detect the signal? They detect the signal, okay, by the differential, means you take the difference of the HR and HS. For example, you use HR minus HS, and this is the changes of heat. Okay, so if there is no thermal event happens in the sample, so HR will be equals to HS. So the heat supply to R and S is the same, so you will not have any changes in heat. So when you have a thermal event, so what kind of thermal event? So let's say melting is a thermal event, evaporation is a thermal event, okay, boiling is a thermal event, TG, glass transition temperature, is a thermal event. Once you pass through any of these events, then you will have the value of heat change, okay, and then the signal will be detected. So let's take melting as an example. You know what is the meaning of melting? When you have a solid, okay, and it passes through the melting temperature, it will become liquid. Okay, so what is the signal of the DSC will look like? Let's say you have a graph, okay, of temperature in the x-axis. Okay, you change the temperature from 0 degree to 200 maybe, okay, and you have a solid with a melting at around 150 degree Celsius. The solid, the one that is straight here, have a 150 degree Celsius, let's say. So if you heat both this reference and sample, when there is no thermal event, you will expect to have nothing change. Okay, this is the H. Okay, nothing change. Okay, so let's say here is 100, here 150, here 200. Okay, but once the heating, I mean the temperature increase up to 150 degree, the substance or your sample start to melt. Okay, and when they start to melt, they start to absorb heat. Okay, so you have a HR and HS. HR minus HS, there's a value. Okay, so means HS, they absorb heat. Okay, and after the melting has complete, okay, means after the thermal event, your HR again at that moment minus HS when they are already in liquid state is equals to 0 because there is no more thermal event. So your signal will go back to a baseline and continue up to the temperature that you have set previously. Okay, so this is how a DSC signal look like. Okay, when you have a melting event, so before the melting there's no event happens. Okay, when you start melting there is a sharp decrease in the signal and then you go back to the baseline. Okay, so now melting is a process that absorbs heat, so it is a endothermic process. Okay, endothermic process. So in this curve here you should label endo down. So any signal that show a down peak is endothermic process. Okay, so here's the definition of DSC. It is a thermal, okay, heat analytical technique in which the difference in amount of heat required to increase the temperature of a sample and reference are measured as a function of temperature. Okay, both the sample and reference are maintained at nearly at the same temperature throughout the whole experiment in order to identify the changes. So let me tell you why you have a sharp peak in the DSC thermogram if a solid melts. Okay, as you know, if a solid melt, do you think they are amorphous or they are crystal? Okay, if you recall the crystal structure, okay, when they have the same long range order of the molecule, means they have the similar, no, exactly the same intermolecular forces within the whole structure, right? They have the same intermolecular forces. Okay, so this force, for example, this force is 5 kilojoule per mole. Okay, let's say it's 5 kilojoule per mole, one force here. And if the heat that's supplied by the DSC is equals to 5 kilojoule per mole, and your bond break, right? And say you have how many bonds in the crystal structure? Let's say we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and we have 12 bonds to be broken, okay, at this point. So that's why you have a dramatic or an obvious thermal event, which you see from the DSC thermogram. That is a straight line beginning, that nothing happened. When you achieve your melting point, you have a sharp endotherm. That is go down, endotherm down. Okay, and they go back to their baseline after. So here is after complete melting. Okay, here is complete melting, and here, okay, here is onset of melting. Okay, understand? And here we have some example of paracetamol. Okay, let me change the ink of the color. Okay, so paracetamol, as you know, that I have mentioned in your previous lecture, paracetamol have different form. How many form? Form 1, form 2, and form 3. Okay, in this particular sample, it shows a temperature, melting temperature at onset of 155. Okay, and at this onset of 155, it is form 2 paracetamol. It is a melting of form 2 paracetamol. And when you look at the onset of 166, it is the melting of form 1 paracetamol. And form 2 paracetamol, they have the orthorhombic shape, and the form 1 paracetamol, they have monoclinic. They are in monoclinic habits, and they are in needle shape. Okay, so you can see different crystal, even though they have the same paracetamol molecule, they show different melting. Here is another example of melting that is detected by DSC, the sample being indomethacin. Okay, and if you are given this diagram, do you think you can tell me what is the onset melting of indomethacin? Onset melting, try to think. And what is the complete melting point of indomethacin? Alright, so the onset means something happen when they start to happen. So when they start to happen, this is the temperature, which is 159.92. And when they have a complete melting, means everything melted, so it is happened in at 16. So besides melting event, other thermal events such as TG, boiling point, degradation temperature can also be detected in DSC. So let's say an amorphous material, they have no melting because the bond is not the bonds within the structure is not equal in strength. So in amorphous structure, there's no melting. Okay, but they have what you call TG, which is glass transition temperature. So glass transition temperature happen in a range of temperature. So for example, when I heat my sample from 0, from here, this is my starting point, I heat my sample, and because amorphous of indomethacin having a TG at 41. So at 41 degree they have a drop in signal, okay, and then they go to another baseline, okay, and this drop in signal is what you call as TG of endomethacin. So you might confuse. In your previous slide we talked about the crystalline structure of endomethacin, and now we talk about amorphous structure of endomethacin. Yes, in every single solid in the world, it can exist in both amorphous and crystal. It depends on how you prepare them. For example, if you leave the amorphous endomethacin for long enough, they will eventually turn back to their crystal form. Okay, so how you know if they have gone back to their crystal? You take some sample from the endomethacin, and then you go into the DSC. Then you examine whether you can identify the TG, or you notice a sharp peak like a melting, and if you see some melting, then there is some crystal in the endomethacin. Okay, so this is the heating process in the thermogram, and in this particular sample we cool it down from 180. We cool it down, and usually when they achieve a similar temperature as TG, so the step will go back to a solid. So here, so TG is a range of temperature, okay, so it happens around 47.4 to, so just now we have done in DSC. So now let's look into X-ray powder diffraction. So let's go into X-ray characterization. X-ray is a type of ray with a certain wavelength that's known, okay, and says now you have a crystal structure like this, okay, and arranged in a 3D long range order, okay. If you look from here, okay, and you will notice it looked like there's a plane here that join those well-ordered molecule. If you look from the bottom, and you might see something like this, okay, there's also in a long range order with plane, okay, we call them plane, okay. And let's say we expose your crystalline material, okay, to X-ray, okay, here is the X-ray source, okay, the ray will go down, okay, hit the plane, okay. When they hit the plane, they will reflect, okay, they will reflect, and they hit the plane, and they will reflect. So they hit like this, and they reflect, and what has been reflected will be recorded by a detector, okay. And because of their well-ordered 3D long range arrangement, that's why they can be detected. So because it is like a wavelength like this, okay, so you have wavelength like this, and then when you go like this, okay, if you look into the wavelength, let's say there's two wavelengths, okay, you have wavelength of here 2, and this one, okay, you will get the amplitude double of the original, but with the same wavelength, okay, same wavelength. This is what you call constructive interference, okay. So when you have constructive interference, it will be detected by the detector, and they will show you the signal will be transformed into a peak. Okay, and this happens when, let's say, your X-ray come in a certain angle here. Here is a certain angle, and you have a same certain angle. So at this angle, the detector will detect a peak, a constructive peak at this angle, for example 5. Okay, and when we change the X-ray source, okay, and the X-ray, they will come in from a different angle, for example 10 angle. Okay, and if constructive interference has happened, and you will get another peak at 10 degree. This is how an X-ray being recorded. So if you are still blurred about the X-ray diffraction, here I repeat briefly. So when you have your crystal structure like this, okay, due to the arrangement that is well ordered in 3D dimensional arrangement, they have the plane in 3D order. Okay, please remember, in 3D order. And when you have your X-ray detector, and this X-ray detector is movable, okay, so they will come in this way. For example, they come in and they will be refracted. The signal of the X-ray will be refracted. Okay, and you have the ray like this, and only constructive interference will be recorded by the detector. So here we have a detector. Only constructive interference will be recorded by the detector. So for example, you want to measure your you want to expose your sample to X-ray, and you have to tell the technician from which angle that you like to see, what is the range of the angle. For example, I want to look at 3 degree up to 20 degree. Okay, so in such a case, the angle will change from 3 up to 20 by moving the source of X-ray. Okay, and when the detector recorded the signal, and you have a curve like this, whereby in the x-axis you label F degree, and the y-axis is the intensity of the signal. What signal? The constructive interference X-ray signal. So let's say at 3 degree you have a peak, at 20 you have another peak. Then here, from looking at this curve, you know it is a crystal structure. Okay, and do you think they are amorphous? No. Okay, they are not amorphous, because amorphous doesn't have the 3D long range arrangement of the molecule. So in amorphous, you can hardly find any constructive interference. So if you can't find any constructive interference, so the detector will only show you something like this. Okay, there's no peak. They will just show you something like this. If you look at the diffractogram, okay, this is what you call diffractogram. If you look at the diffractogram of X-ray like this, which you call them, you describe them as halo pattern, then they are amorphous. Okay, and if you found that the diffractogram shows some peak like this, then they are crystal. So here we define X-ray. So X-ray diffraction is used to obtain structural information about crystalline solid. So it is a gold standard method in determining crystalline solid. Okay, it is useful in biochemistry to solve the 3D structure of the complex biomolecule. Okay, so the wave interact with a solid. Okay, they scattered the beam and interference constructively in some direction and produce diffracted beam. Okay, so when they produce diffracted beam, then they will produce the peak, as I mentioned before. So if random arrangement cause the beam to randomly interference and no distinctive pattern is produced, that's why you have what you call something like this, a halo pattern, usually for amorphous material. Okay, so for crystalline material, due to the regular pattern of the crystal atom, produce regular diffraction pattern. Okay, and this pattern can give information on the crystal structure. Okay, how they give the information of crystal structure? Actually, in X-ray diffraction, it is bound by Bragg's law. Okay, so the equation of Bragg's law is they are trying to relate the wavelength here, the lambda wavelength equals to 2d sine theta. So you have the theta, right? And you know the wavelength of the X-ray. So whatever that you don't know is just the d. What is d? D is the spacing, which is here to here is a d, the spacing of the crystal. So if you know the spacing of the crystal and the angle, perhaps you can actually imagine the real structure of the crystal. This is just a schematic of how X-ray functions. So you have your X-ray beam here, okay, and they can come in with different angle, okay, different angle, and when they shine to the crystal and it diffract, okay, when they diffract means they recorded some peak here. So this is some example of the result of X-ray. So what you call the result of X-ray, just now I have mentioned to you, result of X-ray is you call it as diffractogram. Alright, diffractogram. Okay, when you see the peak like this, they are for sure crystalline material, and this one also, they are for sure crystalline material. Okay, and if you look at it, okay, this is an anhydrous crystalline epicillin and this is a hydrate crystalline epicillin. Even though they have different polymorph form of the crystal structure, you will have different pattern of diffractogram. This is how you differentiate the solids. Okay, and how you differentiate the crystal from amorphous? As I said, in amorphous you won't have any sharp peak, but you have something like this, which is what you call as halo pattern. Okay, perhaps there's some peak here which you might expect. Maybe there is some contamination of crystal structure, and this contamination of crystal structure here in this particular sample over time. So after we have done with DSC and X-ray powder diffractions, let's go into Fourier transform infrared technique. Okay, so when we talk about infrared spectroscopy, it is a spectroscopy that deal with the infrared region in the electromagnetic spectrum. Okay, and this region, the infrared, they have the they have the wavelength, okay, wavelength of the infrared longer than wavelength of the visible light, and the frequency of infrared lower than the frequency of visible light. And how the infrared spectroscopy function? They function by the principle of absorptions. Absorptions of the infrared energy when the movement of the molecules happen in the same frequency of the infrared. So example, you have a carbonyl bond, double bond, okay, so you should visualize them as like two spring, okay, two spring like this, and they are movable, they are stretchable, okay, and while they stretch, okay, they stretch in a certain frequency, okay, and when this frequency match the infrared frequency, they will actually absorb the energy from infrared, okay, and then we will have the spectrum of infrared like this, for example, and they have a certain intensity, okay. For example, in carbonyl bond, the frequency is around 1500 cm-1, so at around 1500 you will find a sharp peak which is corresponding to the carbonyl bond, okay. Anything happen to the solid, for example, the carbonyl bond is possible to have hydrogen bond interaction with some other atom that having the hydrogen atoms, okay. So in this case, if the stretching pattern of the carbonyl bond change as a result of interaction with the hydrogen atom, then there might be a shift in this peak, okay. You may see the peak shift earlier, okay, and they become maybe 1590, okay. So from there you might know the changes in intermolecular forces from one form to another has occurred. So usually people use infrared spectroscopy to differentiate the intermolecular bonds, okay, to differentiate intermolecular bonds between different polymer, okay. So they will have only how you identify them, they will just have a different fingerprint. Like every one of you, you have a different fingerprint. This is how you differentiate each other. And the intermolecular bonds also you can use to difference the state of solid. For example, we can differentiate amorphous, and we can differentiate as well crystal, because in amorphous, most of the strong intermolecular bond has been broken. So in such a case, we will imagine that there will be some changes in the infrared spectra, okay. So for infrared spectroscopy, the principle behind it, the instrument, I believe that you has already learned in chemistry subject, so I won't go into detail. So after we have done with the three initial techniques of characterizations, which includes the SC, XRPD and FTIR, now let's go into the microscope techniques, which is by observation. So when we talk about optical characterizations of a solid, we need to first understand the word of isotropic, okay, in which that the physical property of an isotropic substance, okay, are actually the same. The physical properties is the same. Properties are the same when measured in any direction. So you have another which is anisotropic, or you can look at it in the way that anisotropic means non-isotropic. So the physical properties of this when measured, okay, are actually different according, okay, the physical property different according to the direction of measurement. Okay, so when you look at the example of a diamond, okay, and when the light passing through the diamond in this way and they shine like this, but when they passing through this way, they are not shining in the same direction, but they shine in another direction, in another direction. This is what you call anisotropics properties. Okay, so truly amorphous solids are similar to gas and liquid, that their physical properties when measured in any direction are the same. Okay, that's why they are isotropic substance. So when you have isotropic substance, they are usually amorphous. Okay, and most crystals are anisotropic, that their mechanical, electrical, magnetic and optical properties varies according to the direction of measurement. Of course, there will be some exceptional, for example, cubic crystal. They are exception because they are highly symmetrical internal arrangement, and that's why for cubic crystal they are still called isotropic solid. So the optical properties of crystals, such as refractive index, are actually controlled by the crystal structure, and usually crystal is anisotropic. Okay, and when they refract the the light in the different direction, you will see something like very shining on the crystal, or you can call as birefringence. This is how people describe the shining characteristic of crystal solid, which is birefringence. So how you detect the anisotropy, which is detected by refractive index changes? Okay, you can use a polarized lens. Okay, to means you can fit the polarized lens in the microscope, and you will observe the shining property of this solid. Then they are crystal. Okay, the refractive index of a light passing through an isotropic crystal must be identical along each of the crystal axes, and such crystals are therefore possess a single refraction. Okay, this is, they are talking about the cubic crystal. Okay, they have only a single refraction, and you didn't see any different in the shining. So like a diamond, okay, you have some blue color, shining white color, they shine differently, so they are anisotropic. So when isotropic, they shine at only one single refraction. So because of the different refractive index for light polarized with the crystal structure, okay, these different in the refractive index will result in the property of double refraction, or what you call birefringence, as I mentioned just now. This is one of the example of image that capture under using optical microscope, that you can see shining property here and there, which indicate crystalline material. Okay, so the same thing here I have the first image and the second image. They are actually the same image. So in the first image, okay, it records I record as a movie. In the first image, I drop a little drop of water on top of the solid, okay, and this solid should be amorphous from beginning, okay, should be amorphous from beginning, and this is what happened at 1 minute, okay, after I drop the water. And if you look into more detail, you can see there are some shining start to grow at the edges of this solid, okay, because when an amorphous, they absorb massive amount of water, absorb moisture, okay, they will increase in molecular mobility, okay, and they will decrease the Tg, and so they will easily turn to crystal, okay. When they easily turn to crystal, if you observe under the microscope, then you will see what you call as birefringence properties, okay. So this is after 5 minutes, okay. So when it is after 5 minutes and you found that this birefringence become stronger and stronger and become more intense, so you know that the particle has changed from amorphous to crystal when they are in contact with water. So after we have gone through the technique of characterizations for solid using DSC, X-ray, infrared and optical microscope, let's go into the last technique, which is using scanning electron microscope. Like a normal microscopy method, an electron microscope actually uses an electron beam to replace the light in producing image, and this technique is particularly useful to investigate the surface morphology of the solid. Alright, an electron microscope passes an electron beam through the object of study and record the electron reflected by the object. Then it will become a SEM method, which is scanning electron microscope. But if the record the transmitted through the object, then it will be the TEM, which is transmitted electron microscope. In the lab, this is how electron microscope look like. Okay, we have a big chamber here, which they beam through the electron here, and you have a sample in here, which is something like a microwave here, and inside is a vacuum. All right, and the signal is recorded in the computer. Okay, and this is the label for the electron microscope, and you no need to worry that you no need to memorize. And this is an example of image produced from electron microscope, and here we found out that we have the polymer in spherical form, and in between you saw this kind of needle shape, and it's a repetitive needle shape. Okay, this is the drug crystal, okay, because they look consistent and systematic throughout the whole sample, where they have this needle shape solid on top of the spherical polymer. And now if the electron beam is transmitted through a sample, it is what you call transmission electron microscope. Okay, electrons have the wave property which are small enough to detect nanoparticle, versus as compared to the light wave, which has a much higher wavelength. So that's why transmission electron microscope is particularly good for small particle. Okay, And in this process, the electrons are shot down through a sample, okay, through a magnetic field, okay, until some of them penetrate through the sample, okay, and the image will show darker region where the electron did not go through, and a lighter region where the electron were absorbed into the sample, okay, and the image analyzed convert the optical image into electrical pulse, and then digitized the pulse to generate the quantitative information and produce a TEM image. This is the example of TEM and how they look like in the lab. Okay, it is quite similar to SEM. Okay, and the different parts is actually labeled here. Okay, and as like SEM, you don't need to worry about remembering every single part of the TEM. It's just for your information. This is the example of image that is recorded from TEM microscopy. So when you see a lighter region, okay, means the electron transmitted through the sample, okay, and if you see dark region, means the electron did not go through the sample, okay. And that's we end the technique of microscopy. So now we have done with all the techniques of characterization, which include DSC, X-ray, FTIR microscope, and scanning electron microscope. So what is the implication of solid characterization to pharmaceutical area? So since the different inter and intramolecular interactions, which include hydrogen bond van der Waals, will be present in different crystal structure and different polymorphs, so they will have different free energy, and therefore they will have different physical properties such as solubility, stability, density, and melting point. Alright, so they will have different type of physical properties. So what? Okay, and the different physical properties of this solid can actually affect the ease of handling of drugs during the manufacturing process. For example, tableting, as we have mentioned in the previous lecture. Okay, and it also determines which dosage form that we should actually design a particular new chemical entities. For example, when you have a powder that is very good for compaction, maybe you will make them into tablet. But if the powder have very poor compaction property, maybe you can design into a capsule dosage form. And also it can affect parenteral drugs, whether the solid is too suitable to be stored as solid, or it can withstand the stability to be stored in liquid form. Okay, and it can inhaler. It can actually affect whether we want to formulate something into inhaler. For example, a dry powder inhaler. It is very important because different particles of the powder, different powder size, will determine where this powder will be inhaled into the lung. Okay, so when we know about the different physical properties of this solid, for example, their solubility, dissolution, absorption, that's why then we can design the drug products, okay, in optimal outcome for the intended use. Okay, as a rule of thumb, the drug product is developed using the most stable form. Usually we use the most stable form, as I have mentioned before, the paracetamol, even though form 2 is better for compressibility. However, form 1 is used in the commercial scale because of its superior stability. Okay, this is to avoid possibility of phase transformation of the metastable form to the stable form. as a result of polymorphism. Okay. So after we have finished the characterization of solids, now we go into the characterization of liquids. Okay, liquid can be characterized with a few parameters, which is number one, viscosity, surface tension, which I will cover in detail later on in subsequent lectures. Okay, it can be characterized by a dielectric constant, boiling point, and vapor pressure. So viscosity. Viscosity is the resistance of a liquid to flow. Okay, it flows by sliding the molecule over one another. So the stronger the intermolecular forces, as you have learned before, the higher the viscosity. For example, you have the viscosity of, for example, syrup. Okay, with a viscosity of 5,000 centipoise, or you have viscosity of honey. Okay, is 10,000 centipoise. Alright, so here you would say the viscosity of honey is more than viscosity of syrup. So the next parameter that you can use to characterize the liquid is surface tension. Surface tension is a result of the net inward force, okay, experienced by the molecule on the surface, means here. Okay, as the molecule on the surface are attracted only by other surface molecule and by molecule below the surface, so there is a net result that, if you can observe the molecule here, there's an imbalance of attraction force because it is only attracted inwards and horizontally. Okay, so the net result is a net downward force. Okay, this create a what you call surface tension. There are several phenomena that you can see from surface tension, okay, whereby the surface tension of water is 7.29 to power of 10 of power negative 2 due to the hydrogen bonding. Okay, so you see there are insects, they can walk on the surface as a result of surface tension. Okay, another example is the molecule mercury surface tension, which is 4.6 10 to power minus 1, okay, joule per meter square, due to the metallic bond. Okay, and this metallic bond is very high, the intermolecular bond is very strong. Okay, that's why most of the mercury what you call shape, they remain like a droplet due to their high surface tension. Okay, liquid can also be characterized by dielectric constant. Dielectric constant is the ability of a material to store electrical charge. Okay, it is a relative measure of chemical polarity of a liquid. For example, water is very polar and it has a dielectric constant of quite high, 78.5, while when we look at the non-polar molecule, which is the M-propanol, it has the dielectric constant of 20.1. Okay, and this information is particularly important when we are intended to do what you call design any separation, or for analytical chemistry in chromatography. Okay, another parameter that can be used to characterize liquid is the boiling point. Is the temperature when the vapor of the liquid is equals to the prevailing atmospheric pressure. If the prevailing atmospheric pressure is 1 atmosphere, it is referred to as the normal boiling point. Okay, and when you bring the solution to somewhere lower pressure, okay, and the boiling point of a certain liquid will be reduced due to their different atmospheric pressure in that particular condition. So there are two main factors that affecting boiling point, which is the first one, external pressure. Lower the external pressure, it will result in lower boiling point. And the second one will be the strength of intermolecular attractions. So liquid that have strong intermolecular attraction will have higher boiling point as compared to liquid that have a weak intermolecular attraction. So liquid can also be characterized by vapor pressure. Okay, vapor pressure is the pressure that the molecule exert above the surface of the liquid at equilibrium. Okay, if no equilibrium achieved, okay, then the liquid will eventually evaporate and dry off. Okay, so for example, any volatile substance, they can evaporate rapidly. So usually liquid that they have high boiling point, they will have a low vapor pressure, and a liquid with low boiling point, and they will give rise to high vapor pressure. Alright, so about the factor affecting vapor pressure, it is first temperature. As the temperature of the liquid increase, vapor pressure increase because kinetic of the molecule increase, so more molecule is evaporated and the pressure increase. Okay, secondly, is the strength of intermolecular attraction. As the strength of intermolecular attraction increase, okay, vapor pressure will be decreased, because when you have the molecule that they are they're having stronger intermolecular interaction in the liquid, so they are less likely to evaporate. Alright, when they are less likely to evaporate, so the pressure decrease. This is just for your information on defining the relationship between vapor pressure and the temperature, as we have mentioned just now in the previous slide, that how temperature can affect vapor pressure, and this equation derive the relationship between pressure and temperature. So the parameter to characterize gas is volume. What's the volume of the gas that you use? The pressure of the gas. Okay, and the ideal gas equation describe the relationship between the volume, pressure and temperature. Okay, and PV equals to nRT, and the N is number of mole of gas and R is the molar constant. This shows the relationship between pressure, volume and temperature. And that's all. Thank you.